Well, it looks like we can get started here. We're about time. I want to thank you all for showing up. I know this is before the start of the conference, so I particularly appreciate your showing up this morning. I'm Mick Peterson. I've got Caleb Dempsey here, and Mackenzie Rockefeller is online, and she's going to do some of the demonstrations of the database. I'm going to start out today by talking about the motivation for this. One of the things that oftentimes gets lost potentially on this is that surfaces are a factor, but they're only one factor. And the question is, why do they fit into the equation? Why is it important to worry about surfaces on a day-to-day basis? And I'm going to heavily depend on Chris Whitten and some other folks who did some very nice work for the International Federation of Horse Racing Authorities, and there's going to be a summary document that came out of a fracture workshop on that. So I'm going to lean heavily on that for the introduction, and then I'm going to go into the specifics of the moisture measurement, since that is going to be the motivation for moisture measurements is keeping the horse safe, and by keeping the horse safe and upright, that's the way we protect the rider. The one takeaway is Leonardo da Vinci said water is the driving force of all nature. And I'm going to say water is the driving force of all racing. That probably is not 100% true for anybody who's got a synthetic track, but anybody who's got turf or dirt, they can pretty much let Leonardo be the lead. So first thing I'm going to talk about is fatigue, failure, and bones, why surfaces matter. I'm going to review the pre-meet inspection. We talked about that. Brandon, Caleb, and Mackenzie talked about that last year, the pre-meet inspection that's done through HISA, and also now is done just about every track in North America at this point is doing the pre-meet inspection. Then I'm going to move on to the daily measurements. We have manual measurements that we've got that we can demonstrate what we're doing here. Mackenzie's going to talk about entering your data in the database. It's set up for all US racetracks, is already set up and is free. Entering that data, so it goes directly to HISA, meets all the HISA reporting requirements. Then Caleb's going to go take over and talk about improved measurement methods, automating this. This is the simplest, but a little bit more labor intensive and additional information that you get out of the integrated surface tester. And then I'm going to talk about some of the things where we go from there: better water trucks, standardized design, real-time moisture measurement. And then once again, I'll come back to this same topic that risk is multifactorial. We can't just fix surfaces. We need to look overall at the risk to the horse and rider. So I'm going to go way off track here for this audience. And I'm going to talk about materials, and this is like metals and ceramics. I'm a mechanical engineer. We're going to talk mechanical engineering here for a little bit. When you move something or bend something and it springs back to its original position, that's elastic deformation. That would be a spring, would be an obvious description of that. When you're using your ballpoint pen, the spring in that, the springs on the back of your car, those springs return to their original position because they're only elastically deformed. That's this little area here. And if you think about it on the spring, you bring the spring, you stretch it out, you return, and when you let go, it's back at the same position you started. Plastic deformation, which if you've got a ballpoint pen, which everybody has one here, you can tear it apart, but I don't think you probably need the exercise. You can pull it apart, and if you pull it too far, it doesn't spring back to its original position. You stretch it beyond the elastic limit, and you end up with an elongated spring. That's the area out here. So this is the deformation, this is the force. So if you continue to pull it apart, it'll stay that way. We normally think about failure like you did something really bad to it, like plastic deformation. What's different about metal and ceramics, as well as we'll talk about bone, is it turns out that if you stay in that elastic region, it's still returning to its original position. You can still make the material fail. You can still move that back and forth, and it will eventually fail. Now, it takes a lot of cycles. It could take a few cycles. It all depends on how much you've deformed that, how much of that elastic limit you've used. So if you're almost to the point where it's going to permanently deform, it's not going to take very many cycles. Out here, we're talking, hundreds of thousands or even a million cycles. At that point, even smaller amounts. So picture this. Even small movements, even small deformation of material can result in failure. Some materials will last indefinitely if you don't load them very much. All right, so what does that mean? It's going to be heavy, okay? It's going to be heavy. You're making a heavy object. What do you think about that for a performance vehicle or a performance animal? That's probably out here is the horse that lost the race. It's heavy. This is using a draft horse to race, okay? You're probably never going to see a fracture. So if bone is subject to fatigue, the real question is, are only horses with low loading or low minimal amounts of training going to be able to be safe? This is an oversimplified model of bone fatigue, however. If we go 10 furlongs, we get a little worse. 20 furlongs, we get a little worse. 30, 40. Injuries happening here, and up here is catastrophic injury. So in that model, you have to get the vet in there quickly between injury and catastrophic injury and make sure that the horse retires before that happens. But the question is this inevitable? Is this model what it looks like? Well, it fatigues like steel. And there's a lot of literature in the human, there's a lot of the human literature that indicates that bone actually does fatigue like steel. And it's also damaged by overload events. You have an event where there is too much load applied for even a short period of time, and you've trimmed away at the life of that bone. But unlike steel, bone can remodel. It's a living tissue. So what's the solution here? Well, obviously part of it is not having those overload events, but the other part is backing off and allowing the bone to remodel and recover because it's living tissue. So we know this again from the human literature, looking at optimal workload. The military spent a lot of time on this, thinking about stress fractures, right? Stress fractures with recruits, they're young, they may not be properly trained, they may not be fit. You're trying to get them fit in a short period of time. So what do you have to do? You have to have optimal workload. Okay, so this is no longer this straight line up. It probably looks something like damage, remodeling, and you're going to look at these damage events. The real trick is to avoid injury, avoid these overload events, and provide recovery time when you do have acceptable amounts of damage. And again, I want to mention, conceptually, I always resisted this fatigue model because it's so oversimplified a living tissue. But Chris Whitten and the other folks at University of Melbourne have actually put together a framework that makes this make sense. So I'm here to talk about surfaces. So why am I talking about bone remodeling? Because if you talk overload events, when we start talking about those overload events, what you're avoiding on the overload events, that's one bad day on the track. The track is not performing up to the requirements on one day. That's an overload event. That's the damage that then needs the remodeling. What can we do in racing to reduce the need and reduce these damage caused by overload events? We've even got a better model of lifetime health. You know, we started out, we took this straight line. What about if we look at this as the life of the horse, not the career of the racehorse? If we look at this as the life of the horse, not the career of the racehorse, we've got an early stage here where we have to build a healthy horse. We have a racing career without severe injury. and then retirement to a second career where you're again stayed out of that injury zone, or at least well below the injury zone that you can recover from. What we're really talking about is we need to protect that horse, and we need to make sure that horse has a consistent surface and appropriate training throughout the career. Training, recovery, and well below that injury rate. The track should not be introducing uncertainty. The track should not be a challenge. The track should not be a challenge for the trainers. The track should not be something that has to be looped back. There are plenty of difficult things that the trainers are doing. Having a consistent track is something that we can do to make the trainer's job easier and to protect the horse. Another thing to remember on this, and this is really important, is this is not all about surfaces. And I'll say that over and over and over. The primary load is muscle-generated force. This is the surface. This is the input. This is the muscle-generated force. What do you know about the muscle-generating force? That's the training of the horse. That's the adaptation. The horse can adapt to the muscle-generated force given time and given the fact that that's going to occur over a longer time period. What we can't do is suddenly increase this surface pressure here, the vertical ground reaction force, and then create problems overall in the loading of the limb. So the way to remember this is the great philosopher Nigel Tufnell said the surface at this point is turning it up to 11. So that's what the surface is doing. We're primarily a muscle-generated force, but the surface can add that little bit more. Okay, so how do we get a consistent surface? There's some things about a surface that change slowly. It's complicated, but turn radius, and especially transitions into the turn, are a factor that may be a risk associated with the horse. Some more recent publications have suggested that turn radius may be an issue. You don't change that very often, right? Only on a major rebuild of the track. Regional climate. You're not going to have the same thing in New York, Southern California, and New Orleans, okay? We're seeing some changes. We're seeing some adaptation we have to make, but it's over a long time period. Other factors that change gradually is we tend to lose material every year from rainfall or breakdown of the material. The base may be damaged, or the turf species on a turf track can change over the course of a year. And then some factors change daily or hourly. Remember, what we're trying to do is avoid those overload events. And one bad race or one bad workout is one of those overload events that can have a long-term effect on the career of the horse. Track temperature on synthetic is one of those. Track moisture on turf or dirt. And then the material consistently moves. You know, gravity keeps the material moving downhill. So every time you go around with a harrow on a dirt track or a synthetic track, you got stuff moving down towards the rail. So over the last 25 years, we've developed the maintenance quality system, which again looks at these same three phases. The long-term, the annual or pre-meet inspections, which would be seasonal, and daily monitoring, the phase 3. This data then goes to a database. Jockey Club Information Systems has data input that McKinsey will be talking about. And then this came out of this was the 2020 rewrite of the surfaces in the NTRA Code of Standards. And then the HISA rules related to racetrack safety came out of that whole piece. Where does this go? Data and support for the non-HISA regulators and track operators, as well as to HISA. So the reason that all of this is in a database and it's stored is it automatically transfers over to HISA for HISA tracks, for non-HISA tracks. Since we're separate, it can go to the other track operators and regulators. Okay, so here, what are the sources of surface variation? Long-term, seasonally, we have base and the base integrity and consistency grades. We have the hard pan that the horse is toe is penetrating down to, that is propelling themselves off of, composition changes, turf, vegetative growth, thatch, and compaction. This infrastructure is basically in place to look at this. Shorter term changes are moisture content, cushion depth, harrowing depth, cushion depth, turf, moisture content, penetration resistance, which can also be related to moisture, but also can have other factors that affect penetration resistance. And synthetic, we have temperature, subsurface compaction, and creep. These are a lot more challenging. The Jockey Club gift, which we received, allowed us to have the infrastructure for standard track testing in place prior to HISA. And that is HISA, the 2154B regulations. Basically, when we come, and HISA has been supporting this for the HISA tracks, other tracks, just about every other track in the US has participated in this. We do the pre-meet inspection for all the HISA tracks. The data automatically is transferred over to HISA. So these 2154B rules are automatically satisfied once the folks from RSTL come, they do the testing, the data is uploaded, and it automatically goes to HISA. What is this? We talked about this, and I'll show you at the end if you weren't here last year. It starts with the OBST, the biomechanical surface testing. This is a standard test. We also do ground penetrating radar to inspect the base. And again, keep in mind, this data is summarized and then goes directly to HISA. And then finally, the grades are measured and the surface grades are measured and compared to the design. And then that is automatically uploaded and compared to the data. So that's the longer term changes. What about the short term changes, these daily or hourly changes? Well, these are also required to be documented. That's the HISA 2154C section of the regulations. Basic infrastructure for meeting that. So the question is, how does a smaller track or a track that's just ramping up meet the 2154C? Or the other way to look at this, how do they keep the most consistent surface to protect the horse and rider? So what I've got here is some of the most basic equipment that we use. This is a relatively low cost, and this actually is an older version of the time domain reflectometry moisture meter. The meter is pressed in, read, and a number is displayed. Most basic version of that, the number is then written on a notebook or a sheet of paper and taken back to the office to enter. This is the Longchamp penetrometer. It is a device with a 1 kilogram mass that drops 1 meter and pushes a 1 square meter rod into the soil. It's kind of cool because it satisfies both the HISA requirement for measuring cushion depth, because you have a weight, you just set it down, you drop it, and you read it before and after. Those measurements are entered, and then the difference is entered into the maintenance quality system. It turns out this same device can be used on the turf as a standard measurement and is right now the only measurement that we have that has been correlated to catastrophic injury of the horse on turf. So in New Zealand, there's a huge data set over a large number of years, which has correlated this to catastrophic injury. So we have these two devices that, walking around, writing down the number, it meets this 2154C or whatever it is. Penetration resistance potentially, and then temperature on the synthetic. One of the things is this requires walking around the track or driving around the track and getting out. But with HISA requirements, it's only 8 points at this point that are required. That's not too bad. You're going to each quarter pole, getting 2 points. If you only have a dirt track, that's a 15, 20-minute job. And it has the added advantage when you're doing it, where you notice things like a washout or a rail that has an uneven point on it. Oftentimes, the track maintenance folks are out there anyway, taking a look at the rail, or at least they should be. And this is a way to help check that. Okay, Mackenzie Rockefeller is going to take over, and she's going to talk about the data input on the maintenance quality system.
Hello, can everyone hear me okay?
Yep.
Okay. Well, hello everyone. My name is Mackenzie. I work for the Racing Surfaces Testing Laboratory, and I've been working with the MQS database for a few years now. If you have used the database, I'm sure we've talked. But so Mick went over how to take the measurements that are required by HISA for the daily surface measurements. And now what do you do with them? Well, RSTL has the database that is free to use for all racetracks. And Caleb, if you could switch to the next slide, please. So the MQS database, it's a tool which gives racetracks a means to electronically record, and that's very useful because you don't have to keep everything in a file drawer for years and years. But you can electronically record and follow useful data from your track to maintain a consistent surface. A consistent surface is important. That's what Mick talked about earlier. But this real-time data that you're getting back from your track, you're seeing it in visual graphs like you're seeing on the screen here, so that you can keep your surface consistent, not only over the whole circumference, but across all the lanes and over time. The MQS does give you the ability to record maintenance entries, so everything done to your track every day. Moisture content readings, cushion depth, penetration depth readings, as well as weather, which is also required by HISA in 15-minute intervals. So we've got everybody covered there. Caleb, can you go to the next slide? So like Mick was saying earlier about the printed sheets, if you wanted to write your measurements down or record your maintenance by hand throughout the day so that you don't forget what your measurements are or you don't forget what was done to that track that day, RSTL has created these PDFs that you can print out and record everything throughout the day, then to enter at a later time, or depending on how your management wants to handle it, you can hand it to somebody in the racing secretary office for them to enter into the MQS. But it has to be entered into the MQS to be sent to HISA if you are a HISA track. It can't just be printed on or written onto these sheets, but they're a great tool to ease the burden of manual data entry. Caleb, next slide. So maintenance records. This is one of the things that's required every single day for your surface, for each individual surface. So whether it's turf, dirt, or synthetic, one of the cool things about the MQS that we've done is have fully customizable equipment lists for every surface at your racetrack. So depending on if you're entering maintenance for your turf track or your dirt track or your synthetic, you'll have a customized equipment list that will pull up. And not only is it different per surface, but it may be different from racetrack to racetrack, depending on what that racetrack calls their equipment. And that's where this local name comes into play. I'm sure everyone's aware that traditions and things are different everywhere you go. So whether one place calls a float a sled harrow, or vice versa, they call their sled harrow a float, or a harrow, a box harrow, etc. But we are actually able to, in the maintenance quality database, delineate between a global name versus a local name, and it'll store that as a global name for us. So Caleb, if you go to the next slide, I have some examples. These are actually screenshots taken from some of the maintenance manuals that RSTL makes for racetracks, which also counts as the racetrack SOP that's required by HISA. And you can find this on the MQS as well. But these are just some examples of how the equipment class can differ from what the track calls that equipment locally. So in the first example, we have a float. It has some teeth on the front, and I think it has the option on the back as well. But at this specific racetrack, they call it a sled harrow. The middle example here, the equipment class would be a roller harrow, but they call it a conditioner. And then the third example, we would call this a roller for the equipment class, where at that individual racetrack, it's called a track packer. So those racetracks would see track packer, conditioner, sled harrow on their equipment list, but we would store them as float, sled harrow, roller. Next slide, please. So for the maintenance records, the users will record all maintenance done to that specific track on a daily basis. You would record things like the date and the time of that specific maintenance, or the time of that specific piece of equipment goes out onto the track. You will record the settings of that equipment. So for example, if you're using a harrow, you would record the depth that the teeth are set at. You would record the direction, whether that's racing or wrong direction, the speed of the tractor, how many rounds versus passes you went. If you're adding water to the track, how many gallons of water did you add? If you're adding sand, how many yards of sand did you add? And we also have different layouts depending on the surface type that you're entering maintenance for. So this example here on the screen is for a dirt track. And Caleb, if you go to the next one. This is an example of a synthetic track maintenance record. And this one looks pretty similar to the dirt track, except for you can see on that far right column on the bottom photo, we have material / amount added. So synthetic tracks may differ from dirt tracks in the fact that they may add specific ingredients of their synthetic at a time. So they may add just bits of fiber or add wax or add gel instead of adding a pre-mixed material to their track. So you have the ability to track exactly what material and what amount and what units that measurement was in for that material that you added. We go to the next one, Caleb. This is a turf maintenance record, and this one will look quite different. We have specific equipment settings. For example, if you're using an aerator, you can enter the depths that the times were set at and the kick percent that the times were set at. If you're mowing, you can put in your mowing height. And the water in this one is not in gallons, it's how long you turn your irrigation system on for. So how many time and minutes did you water? Go to the next slide, Caleb. Moisture content. So moisture content is required for both dirt and turf tracks daily at both the quarter poles at both 5 and 15 feet off the inside rail. The left-hand side picture is a screenshot from the MQS where you can select your track and then look at all records for a given time period. So if you want to just look at one record, you can look at that detail report or click on the pen, the little blue pen under action, so you can edit it or look at the individual record itself. Or if you want to look at the summary report, which is shown on the right-hand side, it'll show you the last 2 weeks of data and it'll put it into a box and whisker plot. So you can see, I like this example here, on August 22nd, that measurement that stands out, there was a lot more variation on this day than there was on any other day in the last 2 weeks. So this makes it really easy for track superintendents to look at data over time and see if anything is changing or if anything jumps out, and then they can look further into it. Well, what maintenance did they do that day? How much rain did they get? Have they changed their maintenance based on what the moisture content is on the track that day? Go to the next slide, please. Like the equipment list and the maintenance records, the location list for both moisture content and cushion depth and penetration depth are customizable. So the default list that comes for all HISA tracks are the quarter poles of both 5 and 15 feet, but that doesn't mean that those are the only measurements you have to take. You can easily take more if that helps you figure out, better data for your track. So I can customize, or anybody at RSPL can customize this location list for you. If you want to take measurements at every 16th pole, at every 8th pole, at different distances off the rail, we can put those in there for you so you can better track what you need to for your track. You will be manually entering the moisture measurements as well as the cushion and penetration depth. So you would choose your location and then type in your moisture measurement based off what you had taken earlier that day. Go to the next one. So this is cushion and penetration depth. You will enter both in the same place, so it'll all be under cushion maintenance. That left-hand side is the same thing you would see on the moisture screen, like I said earlier, so you can choose a track and then choose a date range and see all of the records in that date range. The right-hand side is the same thing. You'll see the last 2 weeks of data for your cushion depth or penetration depth. And so you can see if, the track is varying a lot or if you're keeping it relatively consistent over time. Go to the next one. So again, this list is fully customizable. Obviously, cushion depth is required for dirt tracks versus penetration depth in turf tracks, but you're entering it all into the same place for ease of access. So you would just make sure you're choosing the correct track once you're entering the data. And this is just another example. The previous example is from a dirt track, and this one is from a turf track, just to show you guys the difference. Go to the next one, please. We also have weather data in the MQS. So HISA does require that racetracks keep weather data in 15-minute intervals. So if you do not have an on-site weather station, we do provide free access to 15-minute interval weather data from a weather API from Visual Crossing that triangulates the nearest public weather stations to the latitude and longitude coordinates of your track. So we provide this free for everybody in both table form and charts. And the charts you can actually go in and look at the past 24 hours versus the past 7 days versus the past 30 days if you want to look at trends over time. Go to the next one. Are there any questions about that? So that was just a general overview. I will go into actually entering some example data sets later in the presentation. But if there's any questions right off the bat, I will take them.
All right. Caleb Dempsey is now going to talk about the integrated track tester, which is an alternative way of taking the data on the dirt, turf, and synthetic surfaces.
Good morning, everybody. I hope we're all doing okay today. So like Mick discussed, we'll be talking a little more about the daily measurements and expanding on what both Mick and Mackenzie have discussed. And we are going to kind of talk about the evolution of the daily measurements and what led to the creation of what we are now calling the integrated racetrack surface tester, which is shown here on the table and here on the screen. So we'll hop right on into it. So as far as the HISA regulations go under section 2154, just like Mick discussed, all racing surfaces are required to take daily measurements as well as record the maintenance performed on these surfaces. And these are going to depend on the type of surface you have. So whether you have a dirt track that's going to, be moisture and depth, whereas on a synthetic racetrack, you're going to be talking about temperature and cushion depth. So we have cushion depth, penetration, moisture content or temperature, the local weather, and then of course the maintenance performed. So we'll go into a little more detail about this. So all tracks need to have the weather and the maintenance. That's a given. For the dirt tracks, again, you're just going to need moisture content, cushion depth. For turf tracks, you're going to need moisture content and penetration. I want to distinguish that as opposed to some other methods that we'll be talking about. And then for synthetic tracks, you need to be taking temperature instead of moisture and cushion depth as well. So what do we need to be doing? We're going to be taking these measurements at the quarter poles, 5 and 15 feet off the rail if you are a HISA track. I personally recommend that you take it at least every 16th pole. You'll take 3 measurements. These measurements are typically like 3 feet off the rail, 7 feet off the rail, 15 feet off the rail. Historically, our oldest MQS users, that's what they did. So I'm talking about NYRA tracks, Fairgrounds, Churchill, even Santa Anita. That's what they do is they take these 3 measurements every 16th pole for a total of 48 measurements. So how do we take cushion depth or penetration? Mick had already previously shown us the Longchamp penetrometer. That is one way you can take it on the dirt. And the classic way has been just using a metal ruler. And this has actually been a point of contention between East Coast tracks and West Coast. At Belmont and Aqueduct, for example, they'll tell you, no, you have to step on the track to pack it down, then you stick it down to the base. Well, in California, they're going to be like, no, 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 no. You got to take the ruler and you got to set it down into the track, and you're going to measure to the top of the furrow on the track. That's the ridges left behind. Sorry, not furrow, the ridges. So that's a point of contention. Then, of course, we can use the Longchamp penetrometer. So for the hand depth measurements, we're talking, resolution, at least to the nearest quarter of an inch. That's about realistically how repeatable you can get that as a hand measurement. The Longchamp penetrometer records to the nearest 1/8 inch. So that's what you can do on both the dirt and the synthetic. For the turf surfaces, again, you can use the Longchamp penetrometer. And then historically, especially out in Europe, one of the big tools being used is the going stick. The going stick provides both penetration and shear. However, one of the problems with the going stick, it's user dependent. So I can take the going stick, I can push it into the ground. Well, if I hand it to any one of you in this room, I almost guarantee you that you're going to probably push it into the ground a little different than I am, right? You might give it a little more force than I would. So we have a user dependency that's based on, because of the strain rates in which us applying the force to push it into the ground. And so, I want to take this point too to point out that, as far as meeting the HISA requirements, which for turf courses requires moisture and penetration, that means tools like the Clegg hammer, and then there's a few other tests. So it might be like a shear tester that you push into the ground and you twist it, and that produces a number like a torque. Those do not meet the HISA regulation. So I just want you guys to be aware of that and keep that in mind. So for the moisture content, Mick showed us the TDR. This is a TDR 300. Can't get these anymore, wish you could. They're nice and simple. Now you can get the TDR 250 or the TDR 350. Both will provide the same measurements. Another big tool that's really popular is the Pogo. The Pogo is a great moisture meter in my opinion, mainly because it has great salt correction capabilities. The TDR 250s, the 350s, they actually pretty are influenced by salt content. For example, at Del Mar, right off the coast, get a good breeze. You take the TDR, you go out on the track, you're going to get like 40% moisture content. Well, what would that mean? Well, 50% would actually mean there's standing water on the track, so of course, there's no way we would have 40%. Well, that's all because of the salt content. And the Pogo is not going to be as affected by that much. I think when we maxed out the TDR, adding salt to the racetrack material in a bucket, by the time the TDR was maxing out, the Pogo or the HydroProbe, which is the same meter, it only raised like 5% in the total moisture content. So that's one of the reasons that I really like the Pogo. Another option, which is similar to the Pogo, but slightly different, is the Dynamax ML3 Theta. That probe, I don't have much experience with, but it takes data in the same way that the Pogo or the HydroProbe does, which is using what's called coaxial impedance instead of time domain reflectometry. And we can talk about that more in detail after if anyone is interested. But I do find that you get better numbers track to track using something like the HydroProbe Pogo, and I'm assuming the Dynamax as well. So how do you want to measure temperature on the synthetic racetrack? Well, really, the best option is to have a temperature probe that you can actually physically place into the ground. We want to stay away from the non-contact methods because there is no penetration. into the surface. So I'm talking like, I'm sure we all remember in COVID where you want to walk into a building and they're like pinning the infrared thing at your forehead. You know, I personally have recorded 94 degrees Fahrenheit as my record. I guess I'm dead. But yeah, we want to have that penetration into the top 3 inches of the profile. And why do we care about the temperature? Well, it affects the wax content in the synthetic track. You know, we have always probably heard, you know, there's a morning track versus an afternoon track, right? That's because we have a change in air temperature, which therefore affects the wax. As far as weather data or what data is required for the weather, there's a few points that are really important. One, at least 15-minute intervals, right? That's going to give us the really accurate, really accurate way of knowing the conditions at the time. So for example, you could imagine, well, it wasn't raining 15 minutes before post. And then of course we have the race, which is another 15-minute interval, right? So that's one of the reasons why we want to have this high resolution of the data. The things that you're going to need on there, you're going to need the average temperature over that 15-minute interval. We want to know the average humidity. We want to know what was the average wind speed. I just saw another article the other day. I think it was Aqueduct. They canceled racing because of wind speeds, high wind speeds. Is that right? Anybody see that? Yeah, yeah. So, and then of course, by wind speeds, we also want to know what was the wind gusts, which is something that Aqueduct cared about on that day, clearly. And then probably one of the really most important ones out of all of that, what is the total amount of rainfall received? You know, we often see that, hey, like, you know, oh yeah, we received a 1/4 inch of rain in one day. Well, you know, some people might not even bat an eye if they received that rainfall in 15, 30 minutes. But if that was rainfall over an entire afternoon, that's something we want to know about. That's going to probably changing the surface conditions and how you might even maintain that track if you're expecting rain. That could be the difference between you deciding to float the track or decide to open the track up between races, something that's, you know, Keeneland that deals with, you know, almost every spring and fall meet because of the rainfall that they receive. And then for the maintenance, that'll be literally every time that harrow goes out onto the track, what speed was it at? What depth was it at? You know, for the turf course, did you aerate? Did you not? Did you add any nutrients to the turf track? You know, these are all things that we need to know. This includes material additions. So every time you add water, sand for the turf course, you might be interested in knowing, you know, hey, was I adding any salts to the track, for example, to help with the nutrient uptake? And all of this, as McKinsey had showed and Mick discussed, can be entered into the MQS. You know, so every measurement that you take, dirt, you know, moisture, we're talking about the cushion depths, the maintenance performed, etc. This can be all entered in there, and it's probably the easiest way to be HISA compliant is just by using the MQS. And all of this data that is collected is reported directly to HISA for you. So you don't even have to worry about that. So we clearly have an abundance of tools and options that you can use to meet the HISA regulations, but that kind of started, you know, drumming up some questions. What if there was a better way or an easier way to perform all of these measurements that we need to take on a daily basis that will help us evaluate the surface condition at any given time? So we need to know moisture content, we need to know temperature, we need to know the cushion depth, and we need to know the penetration depending on the surface type. It would be great if we could get away from literally using a pen and pad, right? So electronic record keeping, there is no human data or no human entry, for example, on the MQS. I'm sure we've all punched in on the keyboard, right? You know, you're constantly deleting from, you know, oh, I hit a 9 instead of an 8, right? Well, those things end up mattering. And when you do this enough times, surely you get better at it, but you're also bound to have an error or two during that data entry process. Another thing is right now, we're limited to using reference markers on the track. What are the track? Probably if you're going to be taking measurements. Any guesses? The poles, right? The pole markers, exactly. So, but what if we are not interested in taking data specifically at one of the pole markers? How do we know where we're at on the track? Well, GPS points, right? GPS is going to allow us to take data anywhere on the track and give the track operators information that they need. Another thing that's great about having electronic records, accountability and management. It is really easy for somebody to be, oh yeah, I took the measurements, and they just sat in their office and wrote in, yeah, I think we got a 3.25 inch, here. It does happen. It has happened. Or it hasn't happened at all. And you could be like, well, did you take the measurements today? I didn't get the report. Where is it? And then you already missed that potentially critical information. Back at Santa Anita in 2019, we actually had a delay. The data was recorded, the maintenance protocols, everything. It was handwritten down, but it wasn't entered into the MQS because the guy who did it, he nearly lost his thumb off the back of the float. Well, that data didn't get entered, and then, but nobody was able to sit there and be like, well, where's the data? It's missing. Oh, I guess we just didn't take it. So that's one of the things we're talking about with the management and accountability. The other constraints, working outside is a tough environment for any piece of equipment, especially, you can look at the tractors, the harrows, you're going to see the rust. We're dealing with dirt, we're dealing with salts, we're dealing with rain. It's out in the open, hot, cold, doesn't matter. We needed a tool that was designed specifically for horse racing. A lot of these tools are borrowed. The TDR was, mostly kept in mind for, turf courses, like at a golf course, which is a lot different than what you would be taking for, horse racing. It's completely two different types of surfaces, even though they're both, growing grass. So we want a tool that was, going to be included for something that was designed for horse racing, actually kind of like the Longchamp penetrometer was, perhaps the going stick. We need it to be accurate and repeatable. So, it shouldn't be user dependent. I should be able to hand you any tool, and you and I should get the same numbers. We also want that to be grounded with academic research and literature, right? We want to be able to sit here and be like, yeah, you use the penetrometer. It has links to race times and injury rates on turf courses. That's pretty good, very valuable and powerful. And of course, one of the big things is that this needed to remain open source. This is, a design that anyone in this room could take. And if you have the means or the desire, you can make this tool. We're not trying to lock it down. We want everybody to have this to be, accessible, so you can make it, so you can take those measurements and hopefully improve the consistency of your surface. So with all those considerations, we set out to design what is now called the Integrated Racetrack Surface Tester. And this was funded by Racing Surfaces Testing Laboratory and by a KEDRC grant in 2018. So this has been a 5-year endeavor that got delayed pretty good by COVID, as I'm sure a lot of us had experiences with that. And so this actually concept of this device predated me even, and I started working with the lab in 2017. And so by 2019, it was becoming clear the TDR 300s were being phased out. So we were losing support for those. The going stick was pretty difficult to get into the US market, and we've had issues with those as well. And so in 2019, we set out to start working on this. And so starting out then, I took the Longchamp penetrometer, proof of concept, and I added sensors to it. I added a depth gauge up here to the top, And then we added the pogo or the hydra probe, if you will, to the bottom of this. And I just kind of slung it all together. If anyone's dealt with like RC cars, use an RC car battery just to even power the thing. And that's shown right here in the prototype 1. And it has evolved over the years. And so I will kind of go through each one of these iterations to show you what led ultimately to this device that you see sitting here on the table. So like I said, for the proof of concept, we needed to have a 1 kilogram mass falling from 1 meter, striking a square centimeter probe tip into the ground. We wanted that to be coupled with moisture content, temperature, salinity, GPS points, and of course, having an interface, a way of logging this data and retrieving it. So all of these electronics were readily available. These are something that we could purchase off the shelf, which is really good on the racetracks, especially for those operators, stuff breaks, water pumps, harrow teeth. It is just a constant battle. So we needed to have replaceable parts. And a way to be able to share this data. So we had memory logging, a visual display, etc. But there are some shortcomings with this. You could imagine if we started throwing a bunch of electronics on here, wires start getting everywhere, and you probably wouldn't want to take it through TSA, huh? So we needed to, now that we proved that it would actually work, this was done at Keeneland, and I also took it out to Laurel and Aqueduct as part of the trial running, just to kind of get some data available on different surface types. It wasn't exactly easy to carry around, as I'm sure you could imagine. It became really top heavy, and we didn't even have straps, a place to hold it and carry it. So you were lugging this, it weighed about 15, 20 pounds. You're lugging that around by hand. That kind of gets exhausting after, about 45 minutes or so. And, we needed to expand. We needed a better way. RC batteries was not the way, to go on this. So that led to the second prototype. So we still kept it the same. It is still a 1 kilogram mass falling from 1 meter. The moisture probe worked phenomenally, so we kept that going on there. But we were struggling with the depth measurement. We were trying to keep the sensors safe, if you will. So if you knocked it over, it wasn't going to get damaged or anything like that. And we came up with this tube design. So the idea is that you would just have a tube with mass would fall down into, and we could use, a non-contact method like ultrasound. That has high precision, it can read to millimeter accuracy. But one of the shortcomings on that was that I would start taking readings at 10 a.m. By 11 a.m., there would almost be a 10, maybe 15 degrees Fahrenheit change. And that changes the speed of sound through the air. Air becomes less dense, so speed will, it will move faster or slower depending on that. And even with temperature corrections to account for those changes in airspeed, I ended up being a ½ inch off by the time I got done taking my measurements. So over a 45-minute interval going on a summer day, for example, I was just ½ inch. I'm trying to go for at least an 1/8 inch of accuracy on this. We also tried using a laser, but turns out sunlight is kind of says no to that. It changes the spot size that the laser points out. So the receiver will think it's closer or farther if you shine a light on it versus not. Even when we tried blocking it, that didn't work. And then we tried different external sensors, which was kind of like how on the first prototype, I had one mounted up here, but it turns out you need, pretty good precision with your machining, your tolerances to keep it straight. Otherwise, what would happen is it would bend it. And then now we're no longer getting accurate depth measurements. Another shortcoming with this was that, at this time we didn't have cellular, the ability to upload remotely. We had this great idea. Oh, well, what if we set up what's called a mesh network. Is anybody familiar with mesh networks in terms of communication? You can imagine kind of like a spider web, and all these webs are where they connect to each other, that's considered a node. And so anywhere on the spider web, you should be able to send a data point and it will travel wherever it needs to go to within that web. We thought that was a great idea until big days like the Derby or Breeders' Cup, where TV broadcasting would kind of basically, cut out sections of our spider web, if you will. And so we were actually losing data over the air that way. So which means missing data points. And on a critical day like Derby, you can't be missing any of the data that you collect. So there was a handful of things that were not great about this iteration. The initial design was a tube design to keep everything internal. And then because of the design changes, because of the sensors, we found out, hey, now I'm moving my sensors outside, and that kind of defeated the purpose of actually using the tube design. And it was very top heavy. All the electronics and the weight was mostly up here at the top. This is Mackenzie. You can see that all this extra room and space, it made it taller because I had all these, electronics stored up there, made it really easy to fall over. The handles on it would bend, and then you couldn't actually access inside the electronics enclosure. So there was quite a few factors in this and why this prototype didn't work, but that led to prototype 3, which is the precursor to what's sitting here. And we ended up using an old faithful sensor off the OBST here. It's called a string potentiometer. It's literally just a string. We have it connected to the probe tip, and so that's how we get those measurements. The OBST has had thousands of high impact drops. And we're like, well, we're talking about high impact with a, 2-pound mass basically falling almost 3.3 feet. Why not use that? At this time, we also became cellular enabled. So that means you could be anywhere on the racetrack and you could upload the data. So we no longer had to worry about the mesh network. And even on the big days, Derby, Breeders' Cup, and a few other events, the Preakness, for example, no data loss. It uploaded every single time, which is exactly one of the things that we needed. We also were able to change, the way it was manufactured. So that actually drove the costs down quite significantly to manufacture. But it also had shortcomings with the designs, particularly it was a welded assembly. And I don't know if you can see this photo of the TDR. Actually, it might be this one that I bent straight back out, but you guys see how that's bent? That's courtesy of Dennis Moore. And this got bent, and what if we're talking about something that's falling down rails, or if you bend a rail, that means the mass is no longer going to fall down. Well, that's not going to do you guys very good if it's all welded together. We can't fix it. So we had to move away from that design, which led to, having basically each part of the penetrometer be replaceable. So if you back it over with the truck, if you manage to, bend it, however Dennis did that, then we can fix it and repair it. So that led to the redesign of the penetrometer one last time, the integrated racetrack surface tester. And we took everything that we've learned from these devices and we kind of came together to put it all together and make some of those improvements. Of course, we found more issues with the penetrometer once we got it made and out in the field. For example, this has the sliding mass. Well, this was originally on wheels. Well, those wheels were chewing up the rails, and then the mass would get hard to move, which wasn't very helpful when you're trying to take your daily measurement when it's constantly binding up on you. Manufacturing time was over, 3+ months to make it. That's not very helpful when we're trying to roll something out. And just frankly, didn't have enough field testing. It's one thing for me to go out there and, I might be probably babying it a little more than I should have, where you hand it out to racetrack crew, and they're just gonna, kind of treat it like this was. So that was one of those difficulties, but once we had a few months in the field, changes that needed to be made, bolts breaking, that kind of thing. Everything was upgraded and led to the current version. And we had the cellular connectivity, we had a robust enough design to the point now that we currently have 7 in operation. One at the Massey University in New Zealand. We have one at Churchill, Colonial Downs. We also have one at Oaklawn Park. You see the one here being used here by RSTL, and then the New York Racing Association. They also have a unit, and they get this unit after this presentation. So we have 7 total, and we currently have orders from Keeneland, Del Mar, and Santa Anita are talking about sharing a unit. Keeneland's going to be getting one, Woodbine's going to be getting one, and Century Downs and Century Mile will also be getting a unit. And so, again, there's still shortcomings, right? We just don't have time in the field for this unit, but we have been addressing those as they come. And one of the downsides too is the cost. It is relatively more expensive than, say, the Longchamp penetrometer and the TDR, but we're hoping that the cost will be reduced on that by at least 10 to 20% next summer to make it more affordable for other racetracks. So we collect all this data. Well, what do we want to do with it? Well, we need a visual way to, look at this data and report it. And so as part of this whole process of designing the tool, there's also a need to develop a backend in which could handle this data that you are remotely uploading. And we're talking automatic reports. So within 30 to 90-ish seconds of uploading the data from the device, so you could be standing at the quarter pole, hit the upload button. By the time you get back to your office, you pull out your phone, check your email, boom. You have a report that shows a mapping of your track with colors associated to the measurements taken of the racetrack. McKinsey showed box and whisker plots. So this is Aqueduct over a 30-day period. So they have been taking data routinely, and we can actually sit here and show these changes and show that the track has been staying within the ranges of the data that they've been collecting over the last 30 days. So for them, they have their set number, and you can see that most of their data is falling within the green, which means they're within range or with at least in the typical variation in numbers that they have been seeing over a 30-day period. So this is all accumulated and encapsulated into a database for future use. This data, of course, is sent to HISA if you are under HISA's jurisdiction, and you receive this report directly to your email. We believe in complete transparency. So every single data point that you take on the racetrack, you get that in a CSV file. You can open this up in Excel if you want, and that's included with the report. So it's completely transparent. It's there for you to use and do with what you will, whether you want to share that data, whether you just want to keep it. Maybe you have your own internal record keeping. That's something that you're able to do quickly as well. So there's been some other outcomes of designing and developing the integrated racetrack surface tester. And it turns out that I can take those same very electronics that we're using in the integrated racetrack surface tester, and I can apply it to almost any other platform I want to. And for example, Mick will be expanding on this more, but where I'm talking about, recording what data you are collecting on the racetrack. For example, maybe you want to be tracking accurately how much water you are setting down on a racetrack between races. So at Del Mar, I was able to install basically the integrated racetrack surface tester into the water truck, and I was able to record within plus or minus 50 gallons. Mind you, they can apply upwards of 3,500 gallons just before one race. I was able to track that within plus or minus 50 gallons but before each race, which was quite impressive to be able to do. Some of the weather stations that RSTL offers, again, using the same electronics. So we have this, really very, tool that can be used for multiple purposes. So, of course, again, everything that has been designed, been created, this is all open source. So everyone in this room can go to racingsurfaces.org, which is RSTL's website, you can go to the open hardware and design and you can download the drawing package and some of the programming for the penetrometer, and everything that we design and develop will also be available there. So if you have the means or the desire, you can make one too, or maybe you think something's wrong with this and you can improve on it. It's all available for you there. It's also led to a spin-off company as a nonprofit. We don't have the capacity to design or, build these units and sell them. And that led to the creation of a spin-off company named Rainier Sensing, who actually sells both the Longchamp penetrometer and the integrated racetrack surface tester. So this was developed by racing for racing. There's not many tools out there that have been designed specifically for this purpose. It can take all of the required measurements. So on your dirt, that's the moisture content and the cushion depth. For the turf, that's the moisture content and the penetration. For the synthetic, that's the temperature and the cushion depth on that as well. It's a single tool that can do every surface. So you don't have to be lugging around 2 or 3 devices. If you have, 3 tracks, Santa Anita, they now have synthetic turf and dirt. Belmont's got the same, Gulfstream Park. Now they don't have to have a bunch of tools. They can just do from track to track, taking all of the data. So this is, again, open source, and it's laid the groundwork for the future and the evolution of recording measurements on a daily basis, and hopefully, between races, which something Mick will be discussing here shortly. Are there any questions?
All right, I've got some more slides. I'll try to keep them a little short because number one, I don't think most people have a 90-minute attention span. I know I don't. And also, I want to give some time at the end because Mackenzie will be around at the end. If anybody who's using the MQS has specific questions, she can share her screen. So within the day, we've begun to look at the day-to-day variation, and these data sets that Caleb's talking about can look at the day-to-day variation with the track limiting it. But the thing to keep in mind is these measurements are only done once a day, after training and before racing. What we know, especially about moisture, is during the course of the race card, there can be significant changes. So the real question is how during the race card, if we go all the way back to those overload events, how during the race card do we adapt the maintenance to ensure that the track is as consistent as possible? So some tracks are already going way beyond the minimum with their protocols. For example, they're at Churchill, they take 96 points for moisture, 84 points on the 96 on the main and 84 on the turf track. Again, the integrated racetrack tester will reduce that labor to just one person walking around once rather than having 2 people walk around with 2 different devices and somebody, probably even a third person or one of those people, writing everything down. So the variation within a day, thinking about the 2024 Kentucky Derby, it was floated for the Oaks in training on the morning of the Derby. They had chain harrows behind the floats. It's like a back rake in New York. And then they had switched to harrows mid-card. These are the challenging days. Derby 2024 was a really, really challenging day because the track was drying out over the course of the race card. How do you make those decisions as to when to change? Experience is absolutely critical. And this is why Derby this year was quite successful. But Jamie Richardson is one of those people who can look at the track. One of the risks we've got in horse racing is the age and experience in replacing these folks. So the integrated track tester gives us once. We also need better water trucks and real-time moisture sensors. Next generation water trucks, we're talking about a standard design that can be used. Water truck replacement for racetracks is an incredibly difficult problem. There's not a big market. It's regional. It's not like a tractor where you're using a general piece of equipment. Water truck replacement, and this is one of the efforts that needs to be undertaken. Longer term, then, we need to have data in real time to help the driver control the truck. Where we're headed on this is a hook loader chassis, so the chassis can be leased. The water truck body is owned by the track. That gets the track out of the situation of having to deal with the maintenance of the truck and the aging of the truck. We'll skip through this. The other critical piece on this is having moisture in real time. Caleb used the same electronics that he used on the integrated racetrack tester. He used to demonstrate measuring track moisture at Laurel between races. The problem with this initial design that he had was it was loading up. It'd accumulate material on the bottom of the sensor, and so it'd change over the course of the race. So the barrier issues on this is it needs to be a non-contact sensor. So we've got several options we're looking at on this. We have a research plan that's been committed to, and we're moving forward on it. And we will make use of the existing Internet of Things platform in order to develop this new sensor. A couple alternatives, microwave, visual, and ultrasonic. But the idea is starting January 1st, we will have funding to start moving forward with high accuracy measurements that can be done off of the Harrow in real time, uploaded in real time. This same reporting will come back to the track superintendent over the course of the race card. So if you think of the 2024 Kentucky Derby, between the 4th and the 5th race, you'd get a report in real time that would tell you the moisture content. You begin to make those decisions associated with the changing of the equipment. All right, where we're at right now, HISA and the superintendents are making tremendous progress. We're beginning to see grade measurements and the maintenance becoming much more consistent, especially regionally. What we see is in the Mid-Atlantic region, we're seeing more and more confluence of the maintenance and the track surface advisory group working between the different tracks to make it consistent. When the maintenance became more consistent in Southern California, we saw a dramatic improvement in the track consistency because we had a single group of people working between the tracks using consistent material. However, we still need these better tools for better instruments and this advanced water truck and design. So I want to finish up with talking about reminding you what we want to be a part of contributing to. We want to be a part of contributing. Racing Services Testing Laboratory and our support of HISA has this overall goal of not only keeping the horse sound through a racing career, but preparing the horse for a second career, having that horse retire at a time where that horse can be productive and happy in a second career. This training and recovery, and also eliminating the deviations that come from those overload events, is absolutely critical part of this. This presentation, as well as last year's presentation, is available on the Racing Services Testing Laboratory website. You've got all of our materials that are there. They're recorded, and they will be posted afterwards. So I want to acknowledge the support that's come from this. The Jockey Club has been absolutely critical to this over a long period of time. Churchill's, Naira, Keeneland, NTRA. And this is a great, oops. I love this Derby start. Isn't that amazing? So thank you very much for coming in. Appreciate your patience.